Okay, let us continue then with some of these diode problems using the second approximation. So I'm going to give you another example here. All right, what we have is we have a 10 volt source, okay? We have a 0.33K resistor. And this time we're going to have a couple of diodes here. These are going to be, in this particular problem, these will be identical diodes. This is a silicon diode, and then we have another diode over here which is identical. It is also a silicon diode. All right? So that's the circuit that we're going to basically be dealing with. All right, now look, our task in this particular problem, okay, is to find this current I, and then having found that current, of course, we can find the current, for example, ID1, and then here we can find the current ID2. All right, this could be called the voltage VD1 across this diode, VD2 across this diode over here. All right, now the diodes are the same. I mean, that's key. Diodes really are the same, have the same characteristics. Okay, so therefore we're going to say that ID1 is really equal to ID2. All right, now let's see where we go with this. We're going to use the second approximation. So really what we're going to do is find the current I, once again, by really effectively taking a loop. That's all we're going to do, is take this loop over here. All right, it's very obvious in this particular case. All right, so if we take this particular loop, let's just draw it in, and we travel around the loop. Let's do that. We've got a plus minus across that resistor consistent with that current direction. So going around the loop, what do I have? I have 10. I have minus I times this 0.33K, and then I have this voltage drop across either one of these diodes. The voltage from here to here, it's the same across both diodes. And using the second approximation, that voltage is 0.7. So from here to here, we have 0.7. They are forward bias diodes, okay, having exactly the same characteristics. Okay, so that's a minus 0.7, and all of that is equal to 0. So look, then we have 10, of course, minus 0.7. Taking this to the other side, we have I times 0.33K. 10 minus 0.7 gives me 9.3. And if I divide both sides by 0.33K, that is going to give me I. And if I work that out, I is around about 28.2 milliamps. And then in this particular problem then, ID1 would be half of that value, so it's 28.2 milliamps, that is, divided by 2. So half the current here, half the current here. Okay, a relatively simple problem. Now we have two diodes in parallel with identical characteristics. Okay. Next problem that we're going to consider, once again, is going to be a series parallel type circuit. We've got a source here, which we'll say is 20 volts. We've got a resistor over here, which will give a value of 4K. And let's have a diode here, which is a silicon diode. Okay, so that's a silicon diode. We'll call this voltage across it VD1 plus minus. And then look, let's put another diode over here like this, which is also a silicon diode. And then we'll put another voltage source right here, plus, we'll say that's a 6 volt source, and that is the circuit that we are now trying to deal with. And what we are trying to find in that particular circuit is the current I. All right, now once again this will break down to a very simple problem. It will be just basically taking a loop. If this is our defined current direction here, then of course the voltage across that resistor is plus minus. Now next time, the next video, okay, we will be looking at things called onset of conduction. We won't actually get into that now, but with the onset of conduction we're looking at just the threshold where the diode is about to conduct. Okay. In this particular case, we've got a 20 volt source here which is trying to push current in this direction, and we've got 6 volts which is trying to push current this way. Well, the 20 volts is much bigger than the 6, and so we can perhaps just intuitively look at this problem and see that the current direction is going to be like so. What it means is, though, that this diode here is basically out of the circuit. Okay, it's out of the circuit, it is not conducting. We have a higher voltage this side than we have on this side over here. So this diode is actually out of the circuit. Okay, so the circuit then reduces to really this resistor, this diode, and this voltage source here together with this voltage source over here. So the loop that we now take would be this loop here. If I go around the loop, I've got 20. I've got the drop across that, which is minus I times 4K. I've got the drop here, which is a minus VD1, and then I've got this voltage source going from a plus to a minus, so it's a minus 6, all equals 0. And of course we know that VD1, because we're using the second approximation, is 0.7. We're going to put that information into there and collect our terms together. So we've got 20 minus what? The 6. And then this one here minus the 0.7, okay, take that guy to the other side, is all equal to then I times 4K. So collecting these guys, 20 minus 6, okay, is 14, minus a 0.7 gives me 13.3, and then divide both sides by 4K, gives me the current I. Once again, if I care to work that out, 13.3 divided by 4K is approximately 3.3 milliamps. Once again, and it was just a matter of taking the loop, summing those voltages around the loop, using the second approximation, noting that this diode is conducting, so therefore the voltage across it is this 0.7, putting that information into the loop equation, basically collecting terms and solving for I. Also noting that this diode, okay, is out of the circuit. It is in a reverse biased condition. That is, the voltage on this side is higher than the voltage on the other side. And you know by how much? It's 0.7 volts. Okay, have a look at that problem. Think about that problem. All right. The last problem that we're going to consider for this video is the following. Let's say that we have a voltage source here, 20 volts, and we've got a diode here which is a silicon diode, okay, and we've got another diode over here, and in this case this diode is a germanium diode, and we've got a resistor sitting here which we could say is a 2.2K resistor in this example. And our task is to find this voltage VO, okay? Current direction, like so. All right, we're going to use the second approximation. All right, so let's just note the second approximation for the silicon diode, which we could call VD1 if you like. VD1 is 0.7. For the germanium diode, we'll call that VD2, is what? It's actually 0.3 volts. All right, now what's going on here? Yes, we're going to take a loop, and it's going to be a very simple loop. But look, once this diode is conducting, that's the germanium diode, the voltage between here and here is going to be what? It's going to be fixed at 0.3 volts. Remember, we're using the second approximation. This voltage doesn't get any bigger than 0.3 volts. What does that mean? It means that this diode never comes into the circuit. This diode never conducts because we never reach that 0.7 volts. Okay, this is holding us at 0.3 volts. So really, it's as if this guy is not even in the circuit. And so the loop that we're really dealing with is the 20 volts, the germanium diode, and VO. So it's a very simple loop. If we go around that loop, this is the loop that we're basically considering. If we go around the loop, what do we have? We have 20. We have the drop across here, the germanium diode, which we could say is a minus VD2. And then we have the drop here, which is a minus VO, all equals 0. Well, VD2 is what? 0.3. So we really have a 20 minus 0.3. If I take the VO to the other side, equals VO. So therefore, this output voltage is simply equal to what? 20 minus the 0.3, which is 19.7 volts. Now the key or the trick or whatever you want to say to this particular problem was that once this reaches 0.3, it stays fixed at 0.3, can't get any bigger than 0.3, therefore this diode never turns on. Okay, and this voltage between this point and this point remains fixed at 0.3.